Welcome everybody. Before we can continue with more examples of groups, we need to digress a little bit and learn about these two very important concepts of equivalence relations and partitions of a set. So what is an equivalence relation? First of all, a relation R on any set A is nothing but a subset of the direct product A times A. Now this is a very abstract and somehow frightening definition, but in the following examples we will see that this is very easy to understand actually. And instead of, so any element of this direct product here is just a two tuple of this form here, AB, and if this AB lies in this subset, in the relation we write A tilde B and say A is in relation with B under this relation R. Okay, now look at an easy example. Let A be the set of all students and their teacher or lecturer in a classroom. Then I can define a relation by A tilde B and as a subscript R1. I call two students or their teacher in relation if A has the same height as B. Okay, so if two students, for example, have the same height, I can't wrap my head around the English foot and inches and stuff, so I'll say it in the metric system. If two students have a height of 1.8 meters, they are in this relation here. So they are related by this R. Or even more interesting, if A is in love with B, this also gives me a relation on this set of all students and hopefully the lecturer is not involved. So now you see very concretely that this is nothing to be afraid of, but it's a very natural thing. And now actually the only important kind of relation for us is a so-called equivalence relation. And this is a relation that is defined by three properties. It needs to be reflexive, meaning that each element of the set is in relation with itself. It needs to be symmetric. That means if A is in relation with B, then B is in relation with A. So you can swap A and B around. And it needs to be transitive, meaning if two guys here are related, A is in relation to B and B is in relation to C, then it must follow that A also is in relation to C. Okay, let's see if these two relations here are equivalence relations. For R1 this is pretty obvious. Let's check the three properties. Does a student or teacher have the same height as himself? Well, obviously. So A is related to itself. Is it symmetric? If one student has the same height as another student, then of course the other way around. They have the same height, so it doesn't matter in which order we apply that. So it's symmetric. Is it transitive? Well, of course, if student A has the same height as student B, and student B has the same height as student C, then of course A and C also are of the same height. So this here is an example for an equivalence relation. And actually this is nothing but equality. It could be the same weight, same height, same hair color, whatever. Equality in all contexts you can imagine is always an equivalence relation. And of course, on the set of integers, for example, if I say two integers are related if they are the same, if they are equal, then this also gives me an equivalence relation. Okay, let's look at R2 for one moment and see if this actually is an equivalence relation. This is already difficult. A loves himself. How would we define that? Being a strong narcissist? Don't know. It is definitely, unfortunately, not symmetric. If A loves B, then it needn't be that B loves A, unfortunately. And transitivity is very interesting. If A loves B and B loves C, then does A automatically love C? Well, surely not. And if so, this gives rise to some interesting or problematic triangle situations. So this R2 is definitely not an equivalence relation on the set of all students, including the teacher or lecturer. Here's a different example from geometry. As the set A, we take all the straight lines in the plane and we define a relation. This double point here in front of this means we define this side here by that. We define that G is related to H if the lines are parallel. Now let's check that this is not exactly equality. This is a different example of an equivalence relation. So is a line parallel to itself? Obviously. So we have reflexivity. If one line is parallel to another, then this one is also parallel to that. So it's also symmetric. Is it transitive? Well, yes. If the yellow line is parallel to the red line and the red to the blue, then of course the yellow line is also parallel to the blue line. So this is another example of an equivalence relation here on a completely different kind of set of all straight lines in the plane. Now we look at the so-called equivalence class of an element. So tilde is an equivalence relation on a set and A is an arbitrary element of this set. Then the equivalence class of this element is defined as follows. Here these rectangular brackets A. I take all the elements in the set A that are in relation to A. And this clearly is a subset of A. So I collect all the elements from my set A that are equivalent or in this equivalent relation with my element A. Then A is called a representative of this equivalence class. Actually, I can take any other B and get the same equivalence class. We will prove that in detail a bit later, although it's actually obvious. And now for a very, very important concept that I had troubles with in the beginning when I learned about this for the first time. This is, I would say, one of the most important ideas or concepts of elementary abstract algebra. We can take the so-called quotient of this set by this equivalence relation tilde, or the factor set of A by tilde, or also called A modulo tilde. This is simply defined as all the equivalence classes where the A run through the whole set capital A. Be aware, this is no longer a subset of A because those are different objects. Those are sets themselves. They are no longer elements of the set, but they are sets themselves. They are equivalence classes. So it is very, very important that you really get a grasp of this concept because we're going to need that a lot of times later on. So here's a very elementary, but I think very helpful example. This helped me back in the day to really, for the first time, understand this abstract construction. So we take a set of Lego bricks in your childhood room, for example, and let them be red, green, and blue. Here I sketched some of them. I don't know if those are actually Lego shapes, but that's not the point here. So I have a set of Lego bricks. Those are my elements. This one brick here I call R. It's a red one. This one here is B. This here is G. This would be R2, R3, whatever. Now I can define a relation on this set here by saying A tilde B, or A is equivalent to B, if A has the same color as B. This is clearly an equivalence relation because it is nothing but equality. Having the same color defines an equivalence relation. And now we take a look at the equivalence class of this Lego brick here. This is defined as taking all the elements. Here I write L for Lego, not A, but that shouldn't be a problem. Could also call it A, the set. All the Lego bricks that are equivalent to R. But that simply means all the Lego bricks that are red, because being equivalent to R simply means having the same color as R, and R is red. So you can imagine taking all the red Lego bricks, putting them in a bag, and this is the equivalence class. And now what does the factor set or the quotient look like? L modulo tilde is by definition the collection of all the equivalence classes. So you can really imagine this here is a bag filled with the red Legos, this is a bag filled with green Legos, and this is a bag filled with blue Legos. So we have stripped away or factored away the property form or size and simply say we're only interested in the color. So here we reduce the information. So we get a smaller set, and this here is no longer a subset. It consists, the equivalence classes contain elements, but those bags are no longer a subset of the set, because here the elements are simply Lego bricks. Here we have bags of Lego bricks. And I found it very helpful to always think of factor sets in this way, at least in the beginning. So this is no longer an abstract concept, but you can really visualize it like that, putting things in bags and stripping away some property that is not interesting at the time. So you get the factor set. Okay, now we continue by proving an elementary but very important proposition concerning equivalence classes. If tilde is an equivalence relation on a set A and B are arbitrary elements, then first of all, two equivalent elements always have the same equivalence class. And second, there are only two possibilities. Either two equivalence classes are the same or they are disjoint. This here means, if you're new to set theory, the intersection of those two sets, meaning all the elements that lie in both sets. And this being the empty set means that there are none. So it's not possible that two equivalence classes are different and contain one or two of the same elements. It's not possible. So either the same or disjoint. And in particular, this means that every element of A lies in exactly one equivalence class. Now, to prove equality of sets, it's often easier, if you don't know how to do it in one stretch, to first show that this set is a subset of this here, and then the other way around, that this set is a subset of that. And then the sets, of course, must be equal. We take an arbitrary element out of this set and must show that it lies in this set here. Remember, those are sets, equivalence classes. So what does it mean to lie in equivalence class? By definition, it means that C is equivalent to A. That's the definition of an equivalence class. By assumption, A is equivalent to B, and now we have an equivalence relation. So if C is equivalent to A and A is equivalent to B, by transitivity, C must be equivalent to B. And this by definition means C lies in the equivalence class of B. And of course, the other inclusion is exactly the same, except that you start with an element in the equivalence class of B and just do the same argument. If you're a complete beginner, I would suggest that you pause the video and do this on your own. So this proves that equivalent elements always have the same equivalence class. So here, of course, the intersection could be the empty set. If it is not, we have to show that in this case, then already both equivalence classes must be the same. So if this intersection is not empty, there exists an element lying in this intersection, otherwise it would be the empty set. So I can take an element in this intersection. Lying in the intersection means that it lies in both of those sets. So in particular, it lies in A. So by definition, this means C is equivalent to A. So by property 1, which we just proved, we have that the equivalence class of C is the same as the equivalence class of A. Exactly the same argument for B shows C lies in the equivalence class of B, so C is equivalent to B. So by 1, these equivalence classes are the same, but then it follows that A must be equal to B because they are both equal to the equivalence class of C. So the equivalence class of A and B must be equal. Okay, now for the last statement, A lies obviously in the equivalence class of itself. Well, not obviously, but because the relation is reflexive. So it lies here. If it lies in another equivalence class, then just by this argument here we see that this equivalence class must be the same as the equivalence class of A. So we conclude that A lies in exactly one equivalence class, namely its own. Okay, now here's a very important exercise that will be on this week's problem set. Would highly suggest for you to do it. We take any natural number n, and then we define a relation on the integers by saying A is equivalent to B if this n that we chose before divides the difference B minus A. And you need to show that this is actually an equivalence relation on the integers, and take a look at the equivalence classes. Again, this is very important for important example class of groups that we are going to discuss in the next lesson. All right, to conclude our digression on equivalence classes, there's a little outlook. I am not sure if this is the correct English word. In German it's Ausblick. I'm not sure. So I present to you some facts without going into any details, but I think they are too interesting to be left out. Let's assume we somehow have constructed the natural numbers, which is a not so easy task in itself. You could do it for Neumann's definition using set theory. I'm not going to discuss that here, but let's take the natural numbers 1, 2, 3, 4, and so on, if you want to include the 0, as given. Then the question arises, what are the integers? Well, you could say, I know that. I take the negative numbers, like -1, -2, and so on, but what is -1? And here's a possibility to actually construct the integers only using this kind of stuff, equivalence relations and equivalence classes, and the natural numbers. It goes as follows. You take the direct product of the natural numbers with themselves. So you take tuples of natural numbers, A, B, and C, D, and you define those two to be equivalent if A plus D is the same as B plus C. Okay, now what is the idea behind this somehow strange-looking definition of this relation? Well, this here is the case if the difference A minus B is the same as the difference C minus D. But here we do pretend like we only have the natural numbers and addition. We do not know what minus is yet. We want to construct the integers including minus and negative numbers. So instead of using this, which would involve the unknown minus sign, I use this. So I bring the D over here and the B over there. So this only uses natural numbers and addition. And then actually if you can show that this is an equivalence relation. This is not too hard. And then if you take the quotient of n to the 2, n times n, by this equivalence relation, you end up with the integers. Of course, this is a bit strange if you're not used to that. For example, the equivalence class of this tuple here, 1, 2, is actually the number -1. So now, using only addition and the natural numbers, you have defined what a negative number is. This, I think, is pretty interesting. And this would be the same as 2, 3, 3, 4, and so on. They all give rise to the same equivalence class, and this equivalence class corresponds to -1. The equivalence class of 1, 3 would be -2, and so on. This all depends on this somehow strange definition of equivalence. Now, if you've constructed the integers, you don't need to stop there. You take the direct product of the integers with the integers without a 0. Z star means Z without a 0. And then you take tuples of integers where the second one can't be 0, and you define two tuples of integers to be equivalent if p times s is the same as q times r. So almost the same as here, but now with the product instead of the addition. And then if you take the quotient of this set here by this equivalence relation, you end up with the rational numbers. So only using multiplication and the integers, you can define what division means. You don't have to say, well, 3/4 is a fraction, and you simply define an equivalence relation here and say these equivalence classes I from now on call fractions. So p divided by q would be the equivalence class of pq. And now this becomes pretty clear, because when are two fractions p over q and r over s the same? Well, exactly if this condition holds. You just multiply by the denominator, nominator. I always confuse those two in English. So you multiply by the numbers down there, and then you end up with this condition. This is what is behind this construction. So if you have too much time on your hands and want to know a bit more about that stuff, I would encourage you to actually do the details here, prove that those are equivalence relations, and take a closer look at the factor set and get used to what I wrote down here. All right, to conclude this digression, let's talk a bit about partitions, which are actually the same as equivalence relations. We will see in what sense I mean that. So think of any set, and if you can dissect the set into, let's say, n different subsets that have no elements in common, then this is called a partition. As always, if you are presented with an abstract definition, always try to think of a simple example. I told you the example with the Lego bricks was very helpful for me. So try to think of the set of Lego bricks, and then it's clear they can be divided into the red ones, the green ones, and the blue ones. And this actually is a partition of the Lego bricks. This is what is behind this definition. And actually this is true for most of mathematics. One mathematician once said, behind every definition there's a picture. You just need to find the right picture so that you can really see what is happening there. Well, not behind every, but I think in most times it's helpful if you can find a picture. So what is the formal definition? You take a set, which is of course not the empty set, and then you take a family of subsets. I won't go into any much detail here, but talking of a set of sets can be problematic if you have infinities or infinitely many members. Let's stay away from these problems. So this is why I call this a family and not a set. But it's also okay if you think of it as a set. So you have certain subsets of the set A sub I, and I is an element of a so-called index set. Always think of an easy example. In the Lego cases, we would have red, green, and blue, or 1, 2, and 3. So in most cases, this index set is finite in most examples that we're looking at, but it need not be. It could be an infinite index set. And these AI are non-empty and they are disjoint, meaning that if I intersect two of them, I always end up with the empty set if they are not the same to begin with. So in this example here, this is the picture behind this definition. A1 and A2 have no element in common. They do not overlap. So they are disjoint. And this is the important condition. By taking the union of all these subsets, you must end up with the whole set again. So you're not missing anything. If, for example, this would be the set A, then the purple subsets would not be a partition because I would miss this part of A here. So the union of all those, you take all those together again, must give you the whole set. And this dot here means we have a disjoint union meaning exactly this here. And again, in the Lego example, the set L of Lego bricks can be written as the disjoint union of the red bricks, the green bricks, and the blue bricks all packed together. So LR would be the equivalence class of a red Lego brick, meaning all red Lego bricks, and so on. So now proposition 6 says, partitions and equivalence relations are the same, in quotes, meaning the following. If I start with an equivalence relation on a set, I can easily construct a partition of this set, and the other way around, if I have a partition of a set, this gives rise in a natural way to an equivalence relation on this set. This is what is meant by they are the same. So, if I have an equivalence relation, then I can define this family of subsets simply as all the equivalence classes, which is nothing but the factor set A modulo tilde. And then this is a partition of my set. That's already it. So simply taking all the equivalence classes gives me a partition. You should note that here, if A and B are the same equivalence class, then the set notation swallows those same sets. So AB as a set, now here again I talk of a set, so forgive me for being not exact here. AB as a set is the same as A. So in a set, I have no double counts. Like if I have two of the same elements written in a set, I can discard one of them. So the other way around, if I have a partition of a set, then I define a relation by the following. I say A is related to B, or let's say equivalent. A is equivalent to B if there is an index such that A and B both lie in the same set of this partition. So I must find one index. This here means exists. This is short, the mirrored E means exists. There exists one I in the index set such that A and B are elements of the same subset in this partition here. Then the claim is this defines an equivalence relation on A, and the factor set of A modulo this equivalence relation is nothing but the partition itself. Okay, now if you're learning this at a university level, I would bet that your lecturer says, well, this is trivial. Either he says it's trivial or it's left as an easy exercise. We do the same, but remember there are always solutions to the exercises, to the problem sets. So this is actually a very good exercise because you can find out if your brain already is accustomed with such abstract reasoning. Because this is something that is actually clear if once you have understood it, but for a beginner this might be very, very hard. So please give it a try. It is not as important as, for example, this exercise here, so you might also skip it. But I would suggest that you try it for a bit and see if you already have a good grasp on this abstract reasoning and how to write down these things. All right, that's it for this lesson. Thanks for watching. I hope you enjoyed that. As always, pretty please give a like, subscribe to this channel and help this channel to grow. I would really appreciate that. And I will see you in the solution videos to problem set number 6. Have a good one and bye-bye.